All right, welcome back. So today we're going to talk about that wow moment in video games. You know what I'm talking about. You're playing and you just have to stop and stare at how a sunbeam cuts through a dusty room or how a puddle perfectly reflects the neon signs above it. It looks so real. Well, today we're going to pull back the curtain and break down exactly how they create that perfect photorealistic light. Which really brings us to the core question, right? I mean, look at this. How on earth do computers pull this off? How do they generate light that looks so unbelievably real and do it in real time? It seriously feels like some kind of wizardry, but I promise you, it's not magic. It's just some incredibly clever engineering. Okay, so let's start at the beginning. Section 1, the quest for realism. For game developers, the holy grail has always been photorealism, making the game world look indistinguishable from the real world. And the absolute key to that, the main technique everyone's using today, is called real-time ray tracing.
So what even is that? Well, it's pretty much what it sounds like. Real-time ray tracing is all about simulating how light actually works in the real world. For years, developers used all sorts of clever cheats and tricks to fake things like shadows and reflections. But with ray tracing, no more faking. The computer literally tracks the path of individual light rays as they shoot out from a source, bounce off surfaces, and eventually hit the camera. It's all about recreating physics right there inside your computer.
Yeah, but here's the catch. This quest for perfect realism runs smack into a huge wall. Let's call it the impossible calculation. Because, as you can probably guess, trying to simulate actual reality, well, it takes an absolutely insane amount of computing power. And just to give you a sense of the scale we're talking about, look at this number, 10 million. A single complex scene in a game today can easily have more than 10 million tiny triangles that make up all the objects, the characters, the buildings, everything. And your computer has to figure out what to do with every single one of them. So here's the impossible part. For every single ray of light the computer sends out, imagine it had to check every single one of those 10 million triangles to see if it hit something. It's not possible. Your game would grind to a halt. You'd be lucky to get one frame every few minutes, let alone the 60 frames per second that we expect. The brute force method is a total non-starter, way too much math. So if the brute force way is impossible, how do they do it? Well, every good story needs a hero, and in our story, the hero is a brilliant shortcut. It's called the bounding volume hierarchy, or just BVH. And trust me, this is the secret sauce that makes the whole thing work. Okay, so what in the world is a bounding volume hierarchy? The easiest way to think about it is like a super smart filing system for the entire 3D world. It takes all those millions of triangles and organizes them into this clever structure of boxes inside of other boxes. It's basically like giving every light ray a GPS so it can figure out where it's going to hit something without having to wander around aimlessly. It's all about speed. So here's how it's built. It's a classic divide and conquer strategy. First, step 1, the computer puts one giant box around the entire scene. Then, step 2, it splits that big box into smaller boxes, and it just keeps doing that over and over, dividing the boxes into smaller and smaller ones until finally, the teeniest boxes contain just a handful of those triangles we were talking about. The country, state, city, street address analogy is perfect. It's just a map to find things quickly. All right, so we've built this incredibly detailed map of our game world. Now for the fun part. Let's actually follow a single ray of light on its journey and see how this whole BVH system lets it find its target in like a blink of an eye. And this right here is the moment of genius, the critical decision. When that ray of light starts its journey, the first thing the computer asks is, does this ray even hit the biggest box? If the answer is no, bam! Everything inside that box, potentially millions of triangles, is instantly ignored, just thrown out, gone. The computer doesn't have to think about them at all. But if it does hit the box, then it just moves on to check the smaller boxes inside. This process of elimination is so ridiculously efficient, it can cut out like 99% of the scene for any given ray. It's just an unbelievable shortcut. Okay, so the ray has zipped through the map from the biggest box down to one of the tiniest ones. Now what? Well, now the computer does the one and only heavy calculation it needs to. It's called an intersection test. This is the final mathematical check to see if the ray actually hits one of the few triangles inside that tiny little box. Once it gets a confirmed hit, that's when it figures out the color and brightness for that one little pixel on your screen.
All right, I know that was a lot of talk about boxes and rays and intersection tests, pretty technical stuff. So let's talk about what really matters. What does this all look like to you, the person actually playing the game? This is the on-screen payoff. This is where all that clever math turns into pure magic. Because this whole BVH system is so incredibly fast at finding things, it frees up your graphics card to do the fun stuff. It's not wasting all its power just looking for triangles. It can actually spend that power on making things look amazing. That's how we get truly accurate reflections. That's how we get soft, beautiful shadows that look real. And it's how we get something called global illumination, where light from a red neon sign actually bounces and casts a reddish glow on the wet pavement below. All of this, plus you get higher frame rates, smoother motion, and it even means less grunt work for the artists building these incredible worlds. So when you boil it all down, the main takeaway is this. It's a classic case of working smarter, not harder. This super efficient search system is what lets the computer use its precious power on what we actually care about, making the game world look absolutely jaw-droppingly beautiful, all while keeping everything running silky smooth. But, there's no such thing as a free lunch. As amazing as this technology is, it's not perfect. It comes with its own set of challenges and costs. So to really get the whole story, we need to talk about the price of that perfection. So let's look at the trade-offs. First up, memory usage. That whole map of boxes, the BVH, has to be stored somewhere, and it eats up a ton of super fast video RAM. Then there's the construction cost. Building that map in the first place takes time, and it's especially slow and tricky for things that are moving around, like characters or cars. You also get something called visual noise. If the computer doesn't have enough power to shoot out tons of light rays, the image can start to look kind of grainy or speckled. And finally, and this is a big one, you need the right hardware. This whole thing really only works if you have a modern GPU with special hardware inside called RT cores, which are basically little processors built specifically to do these ray tracing calculations at lightning speed. And that last point about the grainy look actually brings us to a really interesting final question. We know that if you don't have enough rays, the picture can get noisy. So how do game developers fix that? How do they take that noisy, imperfect image and clean it up to give us that crystal clear, cinematic look we see in the final game? Well, that is an awesome question and a topic for a whole other explainer.